Good evening. My name is Christopher Landverde, and tonight we're going to be talking about landslide prevention through the use of retaining walls. Tens of thousands of people's lives are affected every year by landslides. This has to do a lot with population growth, urbanization, the dependency of living in mountain and coastal areas. Unfortunately, no country is safe from the wrath of Mother Nature. The problem is exacerbated dramatically in countries where landslide prevention infrastructures don't exist. One infrastructure that can greatly reduce the death toll caused by landslides is that of retaining walls. Retaining walls are characterized by their ability to retain and restrain material on one side. Retaining walls have been proven to be very effective solutions for landslides because of their high capacity to withstand tremendous amount of lateral pressure when properly built. To increase the success of retaining walls, it is imperative to first understand how, where, and when landslides are more likely to occur. Then it becomes crucial to know the different types of retaining walls and how they each specialize in different scenarios, thus increasing the success of landslide prevention. First, we're going to be looking to how landslides occur. As mentioned previously, landslides are dramatically increasing. Between 2004 to 2016, more than 50,000 people were killed by landslides. This is a direct result of the movement of human activity to areas in coastal and mountainous regions due to the exponential growth of the human population. However, there is no single The short animation clip shows how rain causes oversaturation of the soil, thus causing a landslide. Next, we're going to be talking about the different types of retaining walls. The first one on our list is the gravity wall. Gravity wall relies solely on its own weight in order to stand up and is commonly made of plain concrete. The typical height is from anywhere from 10 to 12 feet. Its massive size allows for it to endure great loads without the need to undergo reinforcement. Next on our list is the cantilever wall. Cantilever walls are the most common type of retaining walls. Recommended heights vary from 10 to 25 feet. They are almost always made of reinforced concrete and work on the principles of leverage. Looking at the figure below, we can see that it includes a heel, which is on the bottom left, and a toe, which is on the bottom right. The long wall is called the stem. Next is the piling wall. Using long underground piles made of steel, this will include soil on both sides of its lower section, as can be seen in the figure. This makes it possible for it to provide high resistance to driving stresses. Some advantages of this type of wall is that they are lightweight and that they can be reused on several projects. Some disadvantages are that they can't be used as part of the permanent structure and that they aren't ideal in areas where huge boulders are formed. Next, we're going to be looking at a case study that highlights just how important retaining walls are and just how effective they are as well. In 1995, in the Conchita region located 80 miles northwest of Los Angeles, California, record amounts of rain caused a massive landslide. This landslide forced thousands of tons of debris, resulting in only the destruction of 9 homes, with no casualties. This forced Californian officials to build a retaining wall in 2000. As can be seen in the picture, this retaining wall was a timber lag pile. This retaining wall was put to the test 5 years after it was built. Again, during the 2004-2005 wet season, Southern California was hit with an intense system of heavy storms. These storms brought in 430 millimeters of rain from December 27, 2004 to January 10, 2005. This caused a deadly January 10, 2005 landslide. This resulted in the destruction of 36 homes, but not only that, it also caused 10 deaths. This was a very serious landslide. Researchers then wanted to see just how effective the retaining wall was in doing its job. So they set out to use an advanced modeling program known as Flow2D. Flow2D was able to model the runout of the landslide. This was done using a digitized pre- and post-event topographic maps, along with model inputs such as an inflow hydrograph and sediment concentration. A series of simulations were then performed in order to evaluate travel path variations for three differing slope configurations present in the area between the 10-year period. The Flow2D program was very successful in predicting the runout of the main lobe of the debris flow. As can be seen, there was the simulation run with no wall at first. As can be seen in the bottom portion of the picture, the two circles show just where the debris flow was occurring. Next, the simulation with a wall was then run. This simulation showed that the retaining wall did in fact do its job, as it prevented and saved many lives that day. As can be seen in the lower portion, the circle with the yellow dots, compared to without the wall, the affected area is much smaller.